Let's go. Hey everyone, welcome for this second session of the Quantum Global Public Goods project of the Quantum Computing Association at EPFL. We wanted to briefly address a recap of what is the scope of the project and basically introduce our speaker of today, which is Ahmed, who will talk about game theory elements. I'll introduce him more explicitly in a second. First of all, just quick reminder about what is the scope of the project. So the Quantum Computing Association this year has decided to establish a project which aims to build some bridges in the research between the concepts, the fundamental concepts of quantum information processing, which are entanglement resources, superposition, quantum algorithms, and a framework which is usually not so well associated to this topic, which is game theory and the theory of decision making. And we shall see that hopefully we have a very interesting ground to address by trying to mix up the notions that Ahmed will present us today in the matter of game theory and trying to address some elements of quantum computing and quantum information processing applications. We shall see how quantum allows us to reach potential new situations and new theory perspectives regarding to this basically all the elements that Ahmed is going to talk to us about in a second. So just to recap about what Ahmed is doing. So he's a bachelor student at EPFL. He's finishing his bachelor in computer science. Ahmed has been in the association for, I think, a year now, if I'm not mistaken. He's also at the origin of one of another big projects in the association, which is a coding project, which is called the Entanglement project. The project scope was to build a non-live version of the IBM board game that was addressed to introduce the fundamental concepts of quantum computing. And we hope that this project will be able to be presented to the EPFL community soon enough. But today he's going to talk to us about elements of game theory on a matter of rather conceptual way and address some mathematical tools as well. The idea is to set the grounds for what will come up next week, which will be addressing variational quantum algorithms and finally addressing the final theory of quantum global public goods game, which is the essential paper that we'll focus on, which will be available on our Slack channel. What more can I say? Yes, it should be all for now. If you have any questions, please don't hesitate to unmute yourself and ask the following questions. And I let Ahmed take the floor for the presentation. Thank you very much.
Thank you, Arthur. So I'm going to share my presentation now. And as he said, this is the second talk in a series of talks that introduces quantum computing to game theory.
Right, I should mention that the first talk we did last week is available on our YouTube channel and was about introducing the concept of entanglement. So a much more physical-based talk. And today we're going to address more mathematical framework, and the idea will be to mix up all those concepts in the following weeks.
Great. So game theory. Well, today we'll talk about the contents. Today we'll talk about the definition of a game in game theory. What does it mean and the terminology necessary. We'll talk about new terms, that is the normal form presentation, the mixed strategy and the pure strategy, and the Nash Equilibrium, which are all familiar terms in game theory that you need to use to understand basic game theory notions. We'll then talk about the prisoner's dilemma, which is a famous game theory problem and has a lot of applications in economics and politics, and also the free rider problem, and also known as the public good and the free rider problem. Then we'll talk about some application of game theory. So what is a game? So a game is a mathematical description of strategic interactions. So we're trying to model the constraint of people and their decisions using math, and then we can solve these problems using math. And game theory has every game in game theory has three main components, which are players, strategy, and payout. So the players are the basic entities who act upon this game. So it could be an individual or a group of people making decisions. So let's take, for instance, they could be business people making a deal together, or it could be a country making negotiations, or it can even be two people playing a game together, like rock, paper, scissors. Then there is strategy. So a player can have multiple actions to choose from, and so he can. So in the example of a businessman making a deal, he can choose to take the deal or negotiate further to make a better deal. And a player's strategy is his or her rule for choosing these actions. So let's say, for instance, a strategy would be something like, okay, if the deal is to I get less than $500, I'll negotiate. Otherwise, I will accept the deal. Then there's the payout. So when the game ends, when a player have made their choices, there's an outcome, and the payout is the number that expresses how good this outcome. So in our example, the outcome would be something like how much money he got. But it's important to keep in mind in game theory that sometimes the payout is not necessarily a number in real life. It's not necessarily like how much he got. Sometimes we could say in a game of rock paper scissors, winning is 1, a tie is 0, and losing is -1. That doesn't necessarily mean I get 1 in real life. It's just important to keep in mind that there's an ordering between these numbers. So 1 is higher than 0, then is higher than -1. That's what's important in these payout to keep in mind. Then there is game factors, and the most important two factors are the timing factor and the observation factor. So timing factor answers questions like are the players playing simultaneously or not? So in a game of tic-tac-toe, they wouldn't be playing at the same time, it's round-based. But at rock, paper, scissors, they would be playing simultaneously at the same time. But it also answers questions like is the game played once or multiple times or an infinite amount of times? There's also the observation factor, which is can other people see my choices or not. Then there's two types of game: cooperative games and non-cooperative games. And the idea is that cooperative games have an external authority enforcing rules of cooperative behavior. This means basically that there's, like for instance, a contract that is binding the two players together, and they can't breach this contract, or otherwise they would go to jail, for instance. So the difference between cooperative and non-cooperative games is that there can be a deal made before these games, and it has to be respected in cooperative games. In non-cooperative games, there is no authority which is able to enforce a contract between two players. So cooperative games are like negotiations, deals, and contracts. So here we have an example of a game. We have two monkeys which were hungry, so they went to hunt for bananas, and they found one single banana on the floor, or an entire stalk of banana on the tree. But the problem is that the stalk of banana on the tree is so high that they can't reach it one alone. They have to be together to reach the stalk of banana. So so they have two choices here. They can either go for the single banana, which is guaranteed they would always get one banana, or they could go for the stalk of banana, which will grant them like 10 bananas. But it's not guaranteed that they will get it, because the other monkey can choose to go for the single banana, and then the first monkey wouldn't get the stalk and he would fall and he would get nothing. So in terms of what we discussed here in this game, the players are the monkeys, and the payout were well, a monkey can get the stalk of banana, which would grant them 10 bananas, or he can go for the single banana, he would get one banana. If both of them go for the single banana, they share it and they get a half each of them. And then he can get nothing if he goes for the banana stalk and then he falls. Well, what is the strategy? It's not trivial here to see the strategy, because you can go say play it safe and go for the single banana, but you can also risk it for the banana stalk, but then the other monkey can decide to go for the single banana. So you see here there's a trade-off. And then also the timing factor, well, as we discussed here, it's simultaneous, because there's a surprise factor. Here there's a leopard chasing them, so they have to take the decision instantaneously and without communicating. So they can't go before at the beginning of the day and say, if we find a banana stalk, we go for it together. They don't have this communication, which makes this game interesting. And then there are observation factors. Well, the monkeys can observe each other's choices. And this is an example of a non-cooperative game. And if it was cooperative, if like they had signed a contract saying, I promise every banana stock I see I will go for with my friend, they would always go for it, and then there would be nothing interesting to analyze here. Now I present something called the normal form presentation. And basically what this says is that, well, we have two players here, the first monkey, monkey 1 and monkey 2. The first monkey can go for the banana stock or the single banana, while the monkey 2 can also go for the banana stock and the single banana. And here inside the table, we can see, well, if monkey 1 goes for the banana stock and monkey 2 also goes for the banana stock, player 1, monkey 1 gets 10 bananas and player 2 gets 10 bananas. So this is the first monkey's payout, and this is the second monkey's payout. On the other hand, if the first monkey decides to go for the single banana and the second monkey also goes to go for the single banana, well, they have to share the banana and they both get a half. If the first monkey goes for the banana stalk and then the second monkey decides to go for the single banana, the second monkey doesn't have to share it, so he gets a 1. But the first monkey falls and then he doesn't get anything and he gets 0. Same thing if for the first monkey goes for the single banana and the second monkey goes for the banana stalk. Sometimes use this notation to make mathematical proofs, and then we write the payout 1. So the payout for the first player, if the first player goes for the single banana and the second player goes for the banana stock, it's gonna be 1. So here we say if the first player goes for the single banana and the second player goes for the banana stock, the payout is 1. Same thing here. If you say for the payout for the second player, if both go for the banana stock, is 10. This is just a notation. Then we introduce a new concept, which is strategy, and mixed strategy and pure strategy. So let's say a player I can choose between n actions. So let's say in our example we have two players. So here n is they can choose between two actions. So player 1 can choose, the first monkey can choose between going for the banana stock or he can go for the single banana. That's the vector of actions he can do. The second monkey also have the same set of choices, so he can go for the banana stock or he can go for the single banana. And then a mixed strategy is an n-component vectors of probabilities. So in our case, the n is also 2 because we have two actions. And then these probabilities are between 0 and 1, and they sum to 1, which is normal in any probability distribution. But what does that mean concretely? So let's say I say the mixed strategy here is 1, 0. This means that the first monkey always has a probability of 1 going for the banana stock and a probability of 0 going to the single banana, which means he always goes for the banana stock. But for instance, if I say for the second monkey is following a strategy half and half, this means that 50% of the time the second monkey is going to go for the banana stock, but 50% of the time he's going for the single banana. The first one is an example of a pure strategy. So a pure strategy corresponds to a vector with one component equal to 1 and the others equal to 0. So it's basically saying it's a pure strategy because there's only one choice I make and the others I never do. And the mixed strategy is mixed because you have multiple probabilities for multiple actions. Then there is the expected payout of strategies. So let's consider a game with two players also, and they have the strategies like we discussed. PA is the probability of the first player doing A, and PB1 is the probability of the first player doing B. Same thing with 2. We say that the expected payout for player 1 is this formula. What does this exactly mean? So this term here is the probability of both players choosing A. So what is the probability of choosing A? Both players choosing A. We know if two events are independent, the union of these events is their multiplication. So the probability of both of them choosing A is the probability of the first player choosing A and the second player choosing A, and then we multiply this with the payout of the first player when AA happens. Same thing with the other components. So we say that Here, it's the probability of first player choosing A and the second player choosing B. We multiply this with the probability of the payout when the first player chooses A and the second player chooses B, etc. So let's take a more concrete example about this. And here we have the formula from the last slide. Here we have the normal form representation that we showed earlier. And then the question is, what is the expected payout for player 1 if it is following the strategy 1-0 and player 2 is following the strategy half-half? So let's calculate the expected payout for the first player. And here, the strategy for the first player, we said it's 1-0. So he goes for the banana stock all the time and never goes for the single banana. While the second player goes half of the time for the banana stock and goes half of the time for the single banana. So let's apply the formula. Here we have probability of the first player choosing A, which is 1. He always goes for the banana stock. And the second player goes half of the time for the banana stock. And the payout for the first player when both players choose the banana stock is 10. We can see it from the normal form table here. When both choose A, the payout for the first player is 10. So we multiply this with 10. Then we go to the next term. What is the probability of the first player choosing A and the second player choosing B? Well, it's also a half. It's also 1 times a half, which is a half. And then what is the payout when the first player chooses the banana stock and the second player chooses the banana? Well, here we can see from the normal form that it's 0. So we multiply by 0. Then we have the probability that the first player chooses B and the second player chooses A, which is 0 because, well, the first player never chooses B. And the probability that both choose B is also 0 because the first player chooses B, never chooses B. So then we get from this, we get the answer is 5, which makes sense, right? Because if we say that the first player always goes for the banana stock, and then the second player goes 50% of the time for the banana stock, and 50% of the time for the single banana, then half of the time he's gonna get 10, and half of the time he's gonna get 0. So on average, he's gonna get 5. Then we introduce the concept of Nash Equilibrium. So given a game with n players, a strategy profile, which what we discussed earlier, which is this vector of strategies, is a Nash equilibrium if the payout for each player. So this is the payout for, let's say, if we replace the I with 1, it will be the payout for player 1 following the strategy Si. And what we mean by S minus I is the strategy of all of the other players. So if we had only 2 players, we would say that this is S2. But let's say we have 5 players. Well, S minus I is the strategy of all the other 4 players. We say that it's a Nash equilibrium if this formula is satisfied. So given that we know the strategy of the other players, our strategy is a Nash equilibrium if this strategy if our payout with this strategy is greater or equal than every other possible strategy. In other words, this is the best that one player can do given the strategies of all the other players. So how do we get the Nash equilibrium for the pure strategy case? Well, here we have we assume that it's a pure strategy Nash equilibrium. So if it's Nash equilibrium, we can see it from the point of view of the first monkey. Well, he can ask himself, what if the first monkey has a pure strategy of always choosing the banana stock? If the second monkey always chooses the banana stock, then I have 2 choices. I can either also go for the banana stock, or I can go for the single banana. But I would rather go for the banana stock because 10 is greater than 1. So if the second monkey always goes for the banana stock, I should go for the banana stock because I get 10 instead of 1. We can do the same thing for the single banana case. If the second monkey always goes for the single banana, I shouldn't go for the banana stock because then I would fall. So I would just go for the single banana and get a half, which is better than 0. But we can also look at it from the point of view of the second monkey. But the second monkey can tell himself also that the other player is doing a Nash equilibrium. So let's assume that the first monkey goes for the banana stalk only. Well, it's the same thing. The second monkey should always go for the banana stalk, not the single banana, because his he would rather get 10 than 1. And also, if this first monkey goes for the single banana, then he'd rather go for the single banana, because this problem is symmetric. So what goes for player 1 goes for player 2. So these are the two underlined. When we have a case with the two parts underlined, this means that it's a Nash equilibria. So these are the two Nash equilibria of this problem. And these two, we can see that they satisfy the definition we have discussed earlier. There is given that one player has a single strategy, we can see that this choice is the best strategy you can take. Now we'll discuss the prisoner's dilemma. And two gang members are arrested, and there's no communication between them. Each of them is held in a cell, but there's no enough evidence to put them in prison. So the officer decided to play a game with them and say that each prisoner can either betray the other by testifying that the other committed the crime or remain silent. So we have 4 cases. If A and B betray each other, each of them will serve 2 years in prison. If A betrays B but B remains silent, A will be set free and B will serve 3 years in prison. And if A remains silent but B betrays A will serve 3 years in prison and B will be set free. And if A and B both remain silent, well, both of them will serve only 1 year in prison. Well, this might seem too complicated now, so let's put it in a normal form. This way it's simpler. So what we basically said that we have 2 players, A and B. If both of them stay silent, they both get 1 year in prison. But if A stays silent and B betrays, well, the first player will spend 3 years in prison because he stays silent, but the other one will go free, so he'll get 0 years in prison. Same thing, if the first player betrays and the second player goes silent, the first player is going to go free and the second one is going to stay 3 years in prison. And if both of them betray, well, they both will get 2 years in prison, which is the worst outcome. If you sum the total number of years in prison, here we'll see that here they both serve 2 years in prison. Here they serve 3. Here they serve 3. And here they serve 4. So the last one is the worst in terms of global good, at least. So let's try and get the Nash equilibrium for this problem. Well, as we did last time, we look at from the point of view of the first player. Let's say he tells himself B can either always stay silent or always betray. So if B always stays silent, player A would rather betray, because if he betrays, he goes free, but if he also stays silent, he'll spend 1 year in prison. Same thing, if B betrays, well, player A would also like to betray, because then he'll spend at least 2 years in prison instead of 3. Now from the point of view of the player B, well, if A stays silent, if B betrays, he'll go free and he won't take 1 year in prison. And if A betrays, B would rather also... I forgot to underline this part. And if B betrays, A would also like to betray. So he'll get 2 years in prison instead of 3. So you can see that the worst outcome is actually the Nash equilibria in this problem. And this is what is so controversial about this part, because why would I even stay silent if I'm always better off betraying someone? Which brings us to the concept of dominant strategies. So let's say we have a player I, a strategy S tilde I is strictly dominant if it results in a strictly higher payout for player I than any other strategy. No matter what strategy the other player adopts, we can write this as a mathematical equation. Well, the payout I for the player I, if he follows the dominant strategy, it's higher than the payout for all other strategies that are not this dominant strategies, and it's independent of this it's independent of this other player strategies. So for all other players' strategy, this inequality should always hold. We can see this here. Well, betraying is we also call in the prisoner's dilemma betraying, defecting, and staying silent, cooperating. So here we say cooperating is strictly dominated by defected, because you should never stay silent, because if the second player stays silent, you'd rather betray, and if he betrays, you'd rather betray. So actually, you can totally remove this line. Why would you stay silent, right? And the same thing happens for player B. Why would I always stay silent? So this is the strictly dominant case. This is why it's the natural answer to take, and this is why it's also the Nash equilibrium. This is the prisoner's dilemma. Now we talk about an extension of this problem called the public good and the free rider problem.
I just have a question before you move out to the extension, just to be sure to understand the math here. So the dominant strategy is for all of the strategies that the others can adopt. So the S minus I, right? But it's but shouldn't it be like, okay, like the dominant strategy is always the payoff is always the best, regardless of my own strategy that I choose. So for all other S of not minus I, but I, which is different from the dominant strategy?
No, so the dominant strategy is the strategy that I choose that is always better no matter what the others choose. So let's erase everything. So here I can have two pure strategies. I can always betray or always stay silent, right? So this is the SIs I can take. And then I look at the S minus I, the other strategies players can take. Well, in the what you're saying is that no matter what I take, I should always have a higher payout. But this is not what's happening here. Oh, you're talking about this part, or
Yes. For me, it seems like this minus I should be a plus. Like
right. I thought you were talking about this one.
no,
Well,
no, for all of the others, I'm okay with this. But the strategy,
you're right.
I think, yeah, okay. Wait,
Yeah,
yeah.
you're right. This is a typo.
Uh-huh.
Right. This should be
Yeah,
a plus I.
yeah, so that means that basically the dominant strategy is like always the best payoff I can get by taking on average all the decisions that the others can make.
Exactly.
I cannot expect them to have the better decision. Okay, got it.
Yes. So we move on to the public good problem, and this is the the problem here. So we have two players, the player one and player two. They can work on or not work to produce a public good that will give utility one to both players, and if at least one player works, the public good will be available for both. And if nobody works, the public good will not be available. And here's the twist: working has a cost C1 for player one and C2 for player two. And we say that this game is uh, we say that well, in this game player one knows his cost, but he doesn't know the other player's cost. So later we're gonna have to make assumptions about these costs. And if you look at the normal form table, we summarize what this problem is saying. So if both of us work, we're gonna have one because we did the public good, but also because since player one worked, he's gonna have to pay his cost C1, and since player two worked, he's gonna have to pay his C2 cost. This is why you have one minus C1 and one minus C2 here. But if player one decides to work and player two decide to not work, well, player one is gonna have the public good, so he's gonna have one, but he's also gonna have to pay for his cost. While player two will only have one, will get one because there is still a public good, but he won't have to pay for the cost C2. In this case, we say that the player 1 is the sucker and the player 2 is the free rider. Same thing can happen while player 1 can decide to not work and player 2 can work. So here the player 1 gets a 1 because there's a public good, and player 2 gets a 1 minus C2. And if both decide to not work, they get both 0. We say also that this is an incomplete information game, so because we don't know a lot about the other cost of the other players. So what to do? How can you analyze this game? Well, the approach, the variant I'm going to explain today is assuming that C1 and C2 are uniformly distributed between 0 and 2. So for the first player, can safely assume that the cost of the second player is uniformly distributed between 0 and 2 and vice versa. And the strategy that each player will do is that the player will only work if his cost is below a threshold T star I. So if player 1 has a threshold T star 1, he's only going to work if his threshold is below this number. And then we start to guess what will this threshold be? What should this threshold be, right? When should I play and when should I not play? So we assume that player 2 has a threshold of T2. We don't know what it is exactly right now, but let's say it's T star 2. So player 1 has two options. Well, if he works, his payout is always 1 minus C1. You have seen this, right? If he works, no matter what the other player does, his output is always 1 minus C1. But if he doesn't work, well, this gets tricky because then his expected payout is the probability that player 2 works. And we said that player 2 works only if his cost is below a threshold T star 2, right? So player 2 works if his cost is below T2. So why is it T2 star over 2? Well, because let's say now the cost is uniformly distributed between 0 and 2, right? Let's say, what is the probability of C being below 0.75, right? We have a number uniformly distributed between 0 and 2, and we want the probability of it being in this interval. But the probability is just this part of this number divided by this number. This is just the law of the uniformly distribution. Well, same thing exactly if we replace 0.75 with just T2 star. Well, the probability of this happening is just this area divided by the entire area, which is T2 star over 2. So the payout if the first player doesn't work is the probability that the second player doesn't work. Sorry, the probability that the second player works, which is T2 star over 2. So the first player will work only if his payout when he works is higher than his payout when he doesn't work, right? Otherwise, he wouldn't work. So if we replace our the numbers we got from the last slide, which is this number and this number, we'll get that he only works if 1 minus C1 is greater than T2 star over 2. And then we can just rewrite this as C1 smaller than 1 minus T2 star over 2, which is the definition of a threshold, right? Player 1 will work only if C1 is smaller than a number. This is the definition of a threshold. So we say that the threshold is just this number. So we have found the threshold of the first player with respect to the threshold of the second player. And then we have then we assume that this game is symmetric. So the first player and the second player have the exact same strategies and the exact same thoughts. So they would both have the same thresholds. And then this is the first equation. We also have the second equation, which we found last slide, which is the threshold of the first player with respect to the threshold of the second player. Can just replace then in this formula this equation, and we get that T1 star is just 1 minus T1 star over 2, which is just saying that 3 times T1 star over 2 is 1. That means that T1 star is 2 over 3 and is also equal to T2 star. So this is the answer to our problem. In this variant, whenever you play, you should have a threshold. So you keep in mind that, okay, I have a cost. If this cost is below 2/3, I work. Otherwise, I don't work. And this maximizes the payout of the players. Now we have another variant where the players play twice. But then we might think that it might be similar, but actually this is different because maybe the information we get from the first day is gonna change the how we play in the next round, right? So we'll have to start from day 2 and work our way back to day 1. This is called backward induction, and it's commonly used in the repeated games in game theory. So on game 2, the game changes because we have information from day 1, as I said. And on day 2 and day 1, the player is still follow the same strategy. So they have a threshold, and if their payout is if their cost is smaller than the threshold, they work, and if it's higher, they don't work. If a player worked the first day, everyone else knows his cost is lower than his threshold. Otherwise, he wouldn't work. So this is just corollary, a result of the last sentence. So then we have these two properties. If the opponent played yesterday, then I know his threshold is high, right? Because uh, if his threshold is high, it's more likely that he played. So he is most probably gonna play again tomorrow. So I should lower my threshold because I know he's probably gonna play. But if I worked yesterday, I know other people are gonna think the same, right? So if I worked yesterday, they're gonna think, oh, this guy has a high threshold, so they're gonna lower their thresholds. And then I have to work because I know they're going to slack off and not work. So you have 4 cases in day 2. In the first case, well, I can say that on the first day, I didn't work and the other player worked. We could have both worked on the first day. Nobody worked, and I worked, and the other players didn't work. So on the first case, where I didn't work and the other player worked, this is the best case for me because then I can really lower my threshold. Because if I didn't work, he knows my threshold is low, and he's gonna have to, and he knows I'm probably not gonna work again. But at the same time, he worked, so I also know that his threshold is high, and he knows that. So he's also gonna think I wouldn't want to work the next day. And there's also the second case where we both work. Well, this case is worse than the first one, but it's still better. I would have a lower threshold than the first day because, well, if we both worked, well, I would still think that, well, he worked the first day, so he has a high threshold, so I should probably lower my threshold. And then there's no when nobody works. Well, in this case, well, nobody worked the first day, so and something bad happened. We all got 0 on the first day, right? So we should probably increase our thresholds if this happened. And then there's the worst case. I worked and the other player didn't work. So in this case, I worked, so the other player knows I have a high threshold, and he didn't play, so I know he has a low threshold. So on the next turn, he's probably gonna not work, and I have to work. We take a side note here and we talk about conditional probability. I'm assuming you know this formula, which says that the probability of an event A happening, knowing that event B happened, is just the probability that A and B happens divided by the probability of B. We have seen in the last slides that the probability that C1 is smaller than T is just C over 2 when we did this part where we get from 0 and 2, and we talked about the uniform distribution. Now we would like to know what is the probability of C1 smaller than T, knowing that C1 is smaller than T prime, right? So we have we have this from the last slide we have concluded these inequalities, right? When I explained why not working the player 1 not working and the player 2 working on the first day is a good thing for the first player. So we can just draw this line again, and then put every threshold in its correct place. So this is the threshold of the first player, of the first player when he didn't work the first day and the other player worked. This is the threshold when they both work the first day. This is the first day's threshold that I'm also gonna call T star for simplicity. This is the threshold if both players didn't work on the first day, and this is the threshold if I worked the first day and the other player didn't work. So these are probably not clear right now why I have these probabilities lined up like this. So let's just take it as an exercise for now, and I'll explain later why we need it. So let's take this guy, and the question is, what is the probability that C1 is smaller than TWW, knowing that C1 is smaller than T day one? Well, the probability that you can use this formula here, and then we would say that what is the probability of A and B happening? Well, TWW is smaller than T star, right? So the probability of both happening is just the probability that T star is smaller, C1 is smaller than TWW. Sorry. And you have seen from this guy, so we have probability A knowing B. The zoom thing is bugging. And then the probability of A and B is just, well, in this case, it's just probability TWW smaller than C1 because TWW is smaller than T star, uh, divided by the probability that, well, T star is smaller than C1. And then if we apply this formula, we just find the answer we have here, which is TWW over T star. If you use this formula right here. But we can also look at it from another angle. Well, let's say, what is the probability that C1 is smaller than TWW? So what is the probability that C1 is in this area right here, knowing that C1 was actually in this area right here yesterday? Well, actually, it's just this part divided by the bigger part, right? We don't need to divide by 2 anymore. We just need to divide by the smaller part because we have this new information from the day one. So this gives us the same answer. Now, what about the probability of C1 smaller than Wn? So the probability of C1 being smaller than Wn, so C1 being in this part right here, knowing that actually C1 is smaller than T star. Well, if it's already here, then it's definitely here, so the probability is 1. Similarly, what is the probability that C1 is in this part right here, while you know that it's bigger than the first day? Well, it's 0, because if we know C1 is in here, there's no way that it's here, so the probability is 0. Now we look at the probability that C1 is smaller than TNN, but we also know that C1 is smaller than T day, so we only look at this part right here. And what we get is just this part right here. So this part is TNN minus T star, and this part is 2 minus T star. And you get this answer. And we'll see later why we need these probabilities to calculate the strategies for the second day. So let's say I didn't work and the other player worked. So in this case, I have 2 choices. I can work, and then my payout is 1 minus C1. Well, if I work, my payout is always 1 minus C1. But if I work, my expected payout is this probability here. It's the probability that C2 is lower than threshold Wn, and C2 is smaller than T day 1. Why is that? Well, let's explain that. Well, we know since player 2 worked, we know that his C2 is smaller than day 1, right? Otherwise, he wouldn't work. So we know that C2 is smaller than T star. And I didn't work and the other player worked. So that means for him, from his point of view, he has the threshold when he worked and the other players didn't work. So we want to see the the probability when the C2 is smaller than the threshold when, from his point of view, he works and the other player didn't work, and knowing that we already know that C2 is smaller than T day 1. And you have seen from the last slides that this is actually 1. So I will therefore never work, right? Because the payout is just the payout if I don't work is 1, and the payout when I work is 1 minus C1, and C1 is just between 0 and 2. So that means that the payout when I don't work is bigger or equal to the payout when I work. So I should there's no reason for me to work. That means that I should set my threshold to 0 to make myself never work. There's the case where we both worked. Well, if I work, my payout is also the same. It stays the same. But if I don't work, my expected payout, well, similarly with the same logic, well, if we both work, this means that on the first day, that means that C2 is smaller than T day 1. And from the point of view of the second player, he should have the C2 smaller than the threshold when we both work too. We have seen from the last slide that this corresponds to TWW over T star, which is what we have here. So I will only work if the threshold when I, the payout when I work is higher than the payout when I don't work, which means 1 minus C1 is higher than TWW over T star, which means C1 is just smaller than 1 minus TWW over T star. So I will only work if C1 is smaller than 1 minus TWW over T star. And as we saw before, this just means that this is the definition of a threshold. So this is the threshold. So my threshold, if we both work, is T star over T star plus 1. Actually, we have to do some calculations still because, well, yeah, my threshold is TWW is 1 minus TWW over T star, right? Let me clear the board so I have more space. So TWW equals, the threshold is just 1 minus TWW over T star. And if you take this to the other side, we have that TWW plus TWW over T star equals 1. And you just do some basic algebra to get the, well, the answer. We want TWW. This is just T star over T star plus 1. Now we have the case where nobody worked. Well, if I work, my payout is always the same still. And if I don't work, well, my expected payout is the probability that the second player works. Well, then when nobody worked, I know that his actually this time his C2 is higher than the threshold in day 1. And but then also, as we said before, I should look from his point of view, and then he should have the probability that C2 is smaller than the threshold when nobody worked. And we have seen in the previous slide that this is the probability we get in this case. We have seen how to go from this part to this part, and then we have also to solve this. So we have this is the, I therefore only work if C1 is smaller than this number. This means that this is the threshold. So the threshold is 1 minus T and N minus T star over 2 minus T star. If I multiply by 2 minus T star on both sides, I get this equation. And then this is T and N minus T star. And then I should just develop the formula. I would get T star T and N equals 2 minus T star minus T and N plus T star. and this remove each other. And if I take a common factor tnn here, I should have tnn 2 minus t star um, I'm sorry. Yeah. And I should also, well, I skipped a step here. Should move this guy to the other side, so I would have 3 tnn minus t star tnn equals 2. You can see that this is just tnn equals 2 over 3 minus t star. I'm running out of space. And this is what we have here. And then finally I have the case where I worked on the first day and the other player didn't work. In this case, my payout is, if I work, is still the same. If I don't work, my expected payout, well, I didn't, this should be a 2 here. I didn't, well, if the other player didn't work, this means that his cost is higher than the threshold of the first day, and then from his point of view, it's he should have he should only work if his cost is lower than the threshold when he didn't work on the first day and I worked on the first day. And we have seen on the previous slide that this probability is 0. So I should always work because, well, on my I should always I know he's never going to work, so I should work. And my threshold is 1, because if I know he never works, I have 2 options. I can work and then I get 1 minus C1, or I cannot work and get 0. And actually, if C1 is higher than 1, well, I wouldn't want to work because then I would get a negative number, so I shouldn't work. So my threshold should be 1. And that's how we should work on day 2. So we should have ourselves the information from the first day. We should have the threshold of the first day, and we should also know who worked and who didn't work on the first day. And if I didn't work on the first day and the other player worked, I should have my threshold to 0. If we both work, we should have our threshold to this number. I should have my threshold to this number. If nobody worked, I should have my threshold to this number. And if I worked and the other player worked, I should have my threshold to 1. But what about day 1? Well, when the game was only played once, the threshold was 0.66. We have seen it's 2 over 3. We won't get into the details of the calculations on how to do the backward induction today, but it's simply 0.59. You can take my word for this one. But why is it lower when the game is played twice? Well, it makes sense because working on day 1 gives information to my opponent about my cost, and that makes him less likely to work on day 2. So working on day 1 doesn't only mean working on day 1 anymore. It means working on day 1 and more probably working on day 2 too. So I should be less motivated to work on day 1. So that's why the threshold goes lower. So this is this is what we're going to explain in this talk about the public goods and how to analyze this version. We can see the application of these games. The first one is the Coca-Cola versus Pepsi Cola, which is the application of the prisoner's dilemma. So we can draw a 2x2 the Nash equilibrium here. And the thing was that there was a study that showed that, not with the exact numbers, but approximatively, that if the player someone is asking a question, does it mean that the threshold is going to be 0 if you have an infinite number of days? Well, actually, this is an even further extension to the public good question, which is, well, uh, which is, sorry, which is now, well, I have seen how to play 2 days, what happens when I play n days. And then when you can generalize to n days, you have to, you make this n go to infinity. But we won't cover this case, this lecture, because it's much complicated. And I'm actually not sure what's the conversions rate with the n case or infinite case prisoner's dilemma. Sorry, public good free rider game. But thanks for the question. And the Coca-Cola versus Pepsi Cola. So it has been said that these two companies can spend money on advertising. So if both of them decide to not advertise, they so this is for Coca-Cola and Pepsi Cola. If both of them decide to not advertise, they both get $500 million each in earnings. If Coca-Cola decides to do advertisements, but Pepsi doesn't advertise, well, Coca-Cola gets $750 million, while Pepsi gets zero. These aren't the exact numbers, of course, but it's just to see how relative these numbers would act. And then if Pepsi decides to do ads and Coca-Cola doesn't do ads, Coca-Cola gets $0, while Pepsi gets $750 million. And if they both do ads, they get $250 million each. So we see that this is very similar to the prisoner's dilemma. We just replaced like the numbers with other numbers, but it's still the same problem, right? We have in this case we have the higher sum, which is 1,000. But if you look at our individually, I should always do ads because it's better than when the other player, no matter what the other player does. So at the end, they both did ads and spent a lot of money on ads, and they both ended up in this case right here. We can also do the parallel with the CO2 carbon emissions for the free rider and the public game. In this case, it's not just two players, it's n players, which are the companies. And then every company can either free ride, which is just continue to emit carbon, and while they want the others to stop doing the carbon emissions. So in this case, the sucker is the people who stop doing carbon emissions, and the free riders are the people who continue to do carbon emissions. And we can easily model this problem using the free rider problem mathematically, and then try to analyze the problems and the strategies and who should work and who shouldn't work, and when is it beneficial to work. So in summary, game theory is a very useful tool to analyze strategic interactions among rational decision makers. And then we talked about the prisoner's dilemma and why is it important. We have seen multiple applications for an application for it. Sorry. And then we have seen the global good problem and the free rider problem, and then we have seen how to analyze it. And then we have seen the variant where we have 1 day and the variant where we have 2 days. And then finally we have seen two applications of game theory, but actually game theory exists everywhere. You can read tons of paper of applications for these kinds of problems, and especially in economics and politics. These are the sources that I used for this presentation, and if you have any question, feel free to ask.
Thanks a lot, Ahmed, for this presentation. Do you have any question for the audience? Just unmute yourself, guys, and ask your questions if you have any. Okay, no question at the moment. So this was really interesting. I wonder, of course, in the CO2 carbon emissions case, for example, we know that there is an asymmetry, right, in the usual strategies, because the cost. So we would the thresholds you were mentioning about in this case would be the cost that would have to be like endured by the countries, for example, to reduce their carbon emissions, right? But we know that the potential damages that will be an outcome of like not preserving the public good, which is of course like reducing the carbon emissions in this case. It would amount not exactly to the damage for the country itself, but maybe to others, right? So there is kind of an asymmetric situation where the fact that the not doing the work like does not affect exactly the threshold in a manner that will influence the others exactly as a bipartite situation, because the situation is not symmetrical anymore. So in this case, does this mean that there is always a threshold that can be found, but it just lowers in terms of, and could be calculated for by case, or would we think about another method to proceed to this arrangement?
From the point of view I have taken, it's a very egotistical approach. So you only look at your payout and nobody else's payout, right? And you try to maximize it. But in the situation of the carbon emission, it's actually the public good we're trying to emulate here. And I think like if we say that stopping carbon emissions actually in this case, because in my case I said that doing the public good gives you a payout of 1, and then you have the cost that gives you a minus C1. Here stopping carbon emissions would have like a cost, and then but the payout wouldn't be necessarily 1. It may be 0 actually. So
Yeah, the payout would not be the same for all the countries, even if
exactly.
to reduce the cost. So you have an additional, you have an additional degree of freedom in this case.
Exactly. Yeah, there is one for you, a more parameter.
I see. Yeah, so this is interesting because now we have these intertwined decisions that have to like not only care, that do not only care about if I work or not, but how much I'm willing to induce, and the estimation of the damages that would be outcome. So we, in the end, if we extend this, so of course here we went for 2 parties, but we extend that for n parties. Each of the decisions of the players would be like into a big matrix in this case, and like a kind of a payoff matrix, and each of the decisions would amount to a different payoff for everyone. And then comes the question of the repetition in this case. You were mentioning through maybe you went through these papers or these examples. Did you see the simulation character that was occurring? Like what were the basic assumptions maybe, or could we have like any papers that do this simulation stuff, trying to like produce all those cases for free rider problem for n parties, or maybe on 2 that would already be useful, just to understand like what are the main assumptions, and if those situations of what we encounter here for our concern of the public good, but maybe other situations that might actually yield different results regarding the parameters.
I can send on the Slack the papers that do this simulation. And regarding what you were saying before, the talking about how now we have like the payoff metrics for end parties. This is where quantum computing comes in, right? Because then you have these intertwined decisions, and then you can entangle them, and
right,
and then you actually in this case you take into consideration everyone, which you can't. I'm not sure you can do normally, right?
Yeah.
In this entanglement.
Yeah. Now the question would be like, is the repetition? So we saw here in the example that doing the repetition decreases overall the expected payoff, right, for each user. So now is the fact that we create correlations between the decisions might actually change this tendency, or in this case, like, okay, my decision is not only now about, okay, what only I would do regardless of the strategy decisions, is the definition of a potential Nash equilibrium in this case. So also, yeah, would it change a bit the framework? I think this is a question we should work out. But there is one question I have, maybe a distinction I have not quite understood between if you come back to the first case of what you illustrated for the Nash equilibrium, you mentioned that there was 2 different Nash equilibriums. Could you explain again what is the main difference between distinguishing a Nash equilibrium and a dominant strategy? Because I always thought that those were like the same, but it's not. There is the Nash equilibrium is more general.
Right. So actually, this is like this is inspired from a problem called the stag hunting problem. So you just replace the monkeys with hunters, and the banana stalk with a deer, and the single banana with a hare, and then you have like a famous problem in game theory. So in here, the well, in a pure strat in the Nash equilibrium, the question you would ask yourself is more like we have this decision here. If I actually changed the strategy, would I be and the other player didn't change his strategy, would I be better off or not? Um, and then in this case, well, in the banana stock, I would go. Oh, should I go to the single banana? No, you shouldn't. And the same thing for the first player. You shouldn't change if you're in this case if the other players aren't going to change their strategies. But in the so that's the definition. So like we know the other player's strategy and it's a fixed strategy. And then our strategy is always better. For the strictly dominant, it's no matter what the other player's strategy is, I should always have my payout higher than the other strategies.
So the strictly dominant strategy is about like securing some kind of payoff, right? Because my question is the following: is the strictly dominant strategy always one Nash equilibrium?
So there's no, because there's, well, depends on how many strictly dominated strategies there are. So let's say in I should go back because here it's symmetric and it goes very well together to only have one here. But let's say we had different numbers and then this for player A had a strictly dominant strategy, so he had the so he could remove this part. Actually, I can make probably an example here. So let's say I have 0 0 and then 0 0 and 5 5 and 5 5, right? Here, well, player A should never do the first choice, right? So yeah, so he should never do this. But then when we look, we have these two are Nash equilibria. So so let's say this is choice 1 and this is choice 2. Choice for player 1, choice 2 is choice 2 is dominating choice 1, but for player B, choice 2 is not dominating choice 1.
Ah, okay. Yeah.
I guess like also when you're asking the question, I don't think it makes sense to compare a strictly dominant strategy with the Nash equilibrium, because a strictly dominant strategy is a strategy profile for one player, like for me, whereas a Nash equilibrium is a strategy profile for everyone.
Got it. So we have this notion of like securing a private payoff between whereas, so this is for the strictly dominant, but the Nash equilibrium says, okay, like now, regardless of the number of players, if one tries to change its strategies regardless of the other, we end up with a global payoff, which is lower than expected. So the Nash equilibrium condition is stronger in terms of public good, public good wise speaking, like if we think about preserving the public good, and reaching a Nash equilibrium is a better thing to always reach out than the dominant strategy for one single player, right?
No, I mean, as a player myself, I would always want a strictly dominant strategy, because that means like it's perfect. Like I can't do anything better.
Right. Yeah, but this does not amount to the public good preservation, right? Because so you might end up with with like a cost which is too high for you, so you decide not to work, and in the end you still enjoy the public good, but the depletion of the public good is still realistic because of the asymmetries in this case. So yeah. Okay.
Well, for this, there's also the notion of a Pareto optimal choice, which this is the one where you can't change a choice's Pareto optimal if there is no other cell in this table where you have a total where like you like have a bigger number for one player and the other players don't go lower. So yeah, it's a tricky definition, but
So could you say it again, just to make sure I understood correctly?
so a cell on in this table would be optimal if there isn't another cell on the table that has a higher number somewhere, and then for the rest of the players it doesn't go lower, right?
So basically, the sum is the highest possible, right? Maybe not, actually, maybe not.
Yeah, it just means that you have two conditions. The first one is that no number goes down in this vector. Well, here it's a two-number vector, so these two numbers don't go down. And the second condition is that one of these numbers go up. And then a cell is Pareto optimal if no cell satisfies these two properties.
Got it. So in terms of okay, so now, but my question would be, okay, now that we're thinking, let's say, okay, we're presenting the quantum strategies in a few weeks. What kind of notions should we aim to reach, like by creating these corporations? Like, what should be the target cost function that we're trying to optimize? Like, in the sense that we want to preserve the public good on a global perspective, right? So we here don't focus so much on the payoff of everyone. We account, okay, for a degree of freedom for everyone because everyone wants to maximize its own payoff. But now that we correlate the strategies, what is the quantity that we should look for? Is it the Pareto optimality? Is this is it Nash equilibrium? Or and then, like, how can we distinguish Nash equilibrium? Because I hear like there are stable and unstable Nash equilibrium, something like this. So I guess this should be a question to keep for next time. What kind of cost function we are looking for? What is the thing we're trying to optimize here on a global perspective? Not, I mean, on the matter of only one player. Because now we accept that if the players agree to, like, you know, correlate the qubits, for example, and create entanglement, so you basically remove some freedom, right? Because you acknowledge that now you're giving some kind of your sovereignty of choosing by influencing your choice by the others. So in this case, this provides, of course, we aim for it to reach a global payoff, which is better. But on average, like this would not be always the dominant strategy for the people. For the individuals.
I think in this case, from the name, I guess, like, we want to maximize global good, right? That means we want to maximize the sum of this vector.
Right. So
like sum of all payoffs.
Yeah. Okay. Yeah. So
we are looking for Pareto optimality. Because basically what happened is that Pareto optimality is the best combination ever, the best situation for everyone. Because something is better in the sense of Pareto if the utility, if the happiness of everyone stay the same and the happiness of someone increase. So what we are looking for is something that it is Pareto optimal, so it's maximize everyone's happiness.
Got it.
And Nash Equilibrium is just a combination of strategies that are optimal in the sense that everyone else cannot choose something better. Okay. And dominant strategy is something that is better than every other strategies.
For yourself.
For yourself. So what we are looking for in terms of public goods is something that it is Pareto optimal.
Got it.
So I have a question: can you summarize Pareto optimality by just maximizing the sum, or can you not?
Yes. If we are taking the if the sum has minus and plus signs, yes.
So it's always a maximization of the sum, right? Or it would amount.
It depends. It depends of what the sum means.
Okay.
If the sums represents the utility, which is the happiness, we want to maximize the sum. But if the sum of the payoff matrix represents penalties, we want to minimize it.
Right.
So basically what happens is that in economy, what we do is we want to maximize utility. But when we translate it into a mathematical problem, we inverse and we want to minimize the cost. Mm-hmm. So when we will read at some articles, we will want to minimize something, but in fact, it is maximizing utility.
Yeah, because of course there are constraints of externalities for one another. You cannot expect to raise and definitely like one big, let's say for a real case where you would have asymmetry, right? Like if I take the example of the carbon emissions of United States versus Bangladesh, for example, if of course the Bangladesh is going to benefit a lot more if the United States decide to commit than the reverse. Like if Bangladesh decides to reduce its carbon emission, it's going to be much less impactful for the US. So in this case, it's not about only like maximizing the payoff for like giving the incentive, okay, the US should pay and Bangladesh nothing, or any other country, but it should be some kind of a scaling problem where everyone is incentivized to keep playing for future iterations, right?
Absolutely. You have the constraint on, you have basically the Bangladesh has to involve sufficiently to make something to the US, mm-hmm. but not too much because it cannot. Yeah, so yeah, you have constraints.
Okay, yeah. So we think about a smart cost function in this case that would take the vector of payoffs and try to reduce it.
Yes.
Got it. Cool. I think that should be enough for today. If there are not any more questions, because yeah, it's getting a bit late. But it was a great discussion. I think we should for next time keep ourselves like, okay, maybe introduce more formal notations for the Pareto optimality as well. Any other questions before I conclude? Okay, no, it doesn't seem so. Anyway, we are still always, we have a dedicated channel on this case on Quantum Global Public Goods on the Slack, so feel free to ask questions for references over there. We'll be gladly sharing everything that comes out of these presentations. Okay, great. Thank you to Ahmed for this amazing presentation, which was very insightful in many ways, very introductory, and at the same time, very mathematical. Guys, for all of those who attended, like, please feel free to give any feedback. Should it be slower? Should it be faster for some reason? Personally, I think that the pace was good, and we had time for discussion also and making sure that we understood the main concepts. So I think this was really helpful. And again, let's keep this presentation, which will always be available on YouTube. We'll gladly sort it out in a few weeks to make sure that we can now relate the quantum version of this game. Let's keep the concept in mind and hopefully see you soon. So next week, I think we'll move to another topic. We'll go back to quantum a bit. We'll introduce, so Sarah is going to present to us variational quantum algorithms, because I was mentioning like just before the notion of cost function, and those algorithms are exactly based on some kind of optimization scheme. So it might prove useful to understand like what is the what a quantum computer can do in terms of maximizing the cost or minimizing the cost function in this case. So we shall see that, and then we come back to the quantum version of the global public goods game, I think in 2 weeks. If not 3, because we might have a presentation in between. Yeah, it might be 2 or 3 weeks, but yeah, this is the schedule for now. Thank you, Ahmed, a lot for preparing this talk. It was really amazing. And again, for everyone else who is interested to join the project or propose an initiative, the Slack is always open. And yeah, that's it. So I will stop the recording right now. Thank you all and see you next week.